Hello, everyone, and thank you for joining the Thomas Expert Series. We're going to get started in just a moment. In the meantime, I do want to ask everyone to make sure their microphone is muted. This Expert Series will be recorded and placed on demand, so please let your colleagues know how much you enjoyed the presentation today. Just to get everyone familiar with the chat, what's the weather like out there? I'm in New Jersey. It's 92 and it's stinking hot and sticky.
100 degrees in Minneapolis.
You got us beat, Frank. It's about 90 some in Pittsburgh. So
Philly's 95.
Wow.
Great in Virginia. Awesome. All right, well, I'll go ahead and turn it over to Mike, the chemistry supervisor, here today to talk about the importance of laboratory water.
hello, everyone. My name is Michael. I've been with LabChem for about 10 years now. So I've been quite involved in a lot of different things, from operations, helping a little bit with sales, helping, more some things with IT, a lot of our product labels. Currently, right now, I kind of manage the day-to-day production and operations within the laboratory, and also helping in the warehouse as well. So I'm going to be sharing my screen here. Then I'll be starting the presentation as well. So. Okay, everybody, I'm thrilled to introduce an intriguing topic that's ever so present yet often looked in our labs, that is water. If you think about it, water is so much more than just H2O. It's a universal solvent, an active participant in reactions, a temperature regulator, and above all, an unsung hero of our laboratory work. Today, we'll be diving deep into the unique roles of this vital element, exploring the importance of water in the laboratory. And no, this isn't just about water being essential to life. This is about water being instrumental to our scientific pursuits, powering countless processes in our daily lab operations. In this presentation, we'll be traversing the broad spectrum of water's functions within the lab, from its fundamental roles to its various forms. We will dive deep into extensive uses and implications. We'll kick things off with the essential roles that water performs, such as acting as a universal solvent, participating in reactions, and helping maintain optimal temperatures. Then we'll take a close look at the different types of water we encounter in our labs: tap water, distilled, deionized, and ultra-pure water. We'll discuss each type's distinct properties, their specific uses, and their importance in maintaining accuracy and reliability in our experiments. Following this, we will dive into the importance of water purity, the methods used to maintain it, and the potential risk of neglecting this crucial aspect. Lastly, we'll wrap everything up neatly with a brief summary of the critical takeaways, followed by a Q&A session to address any questions and thoughts that might arise during this enlightening journey. Let's dive in. So here you guys can see some of the objectives that I just discussed. The pivotal role of water. Water, in its seemingly simplistic structure, is a robust workhouse in our labs. To truly appreciate its contributions, we need to dissect the pivotal role it plays. At a glance, water serves as a universal solvent, enables and participates in countless chemical and biological reactions, and efficiently regulates temperatures. The very nature of water, with its polar molecule and ability to form hydrogen bonds, allows it to dissolve a vast array of substances. This capability earns it the coveted title of universal solvent, a feature we exploit routinely in our labs. Moreover, water isn't merely a spectator in chemical reactions. It often leaps into the action, becoming an integral participant in numerous reactions. And as if these roles aren't impressive enough, water's unique properties enable it to effectively manage heat, maintaining the temperature of our experiments and equipment. It is indeed the multitasking marvel of the lab. Water's unique characteristic of polarity allows it to dissolve a wide range of substances, making it an ideal solvent for creating lab solutions and mixtures. This property, known as universal solubility, is the reason why water is often referred to the universal solvent. It can dissolve substances such as nutrients, vitamins, minerals, and organic salts, making it indispensable in the laboratory. This ability to dissolve diverse substances allows us to create a wide range of solutions and mixtures, enabling us to perform a vast array of experiments and procedures. This is one of the reasons why water is so crucial in the lab. It's not just about the fact that water can dissolve so many substances, but also how it does so. The polarity of water, which arises from the difference in electronegativity between the hydrogen and oxygen atoms, causes it to have a slight charge. This charge allows it to interact with other charged particles, such as ions, enabling it to dissolve them. This property is fundamental to many processes that take place in the lab. Water is not just a passive participant in chemical reactions. It often plays an active role. It is involved in common reactions such as hydrolysis and hydration, where it interacts with other molecules to facilitate these reactions. It is vital in the preparation of solutions and suspensions, acting as a medium in which other substances can interact. It also partakes in many reactions, often being consumed or produced in these processes. Furthermore, due to its unique properties, it is used in biological and chemical assays, where it facilitates the interaction of different biological and chemical entities. This active role of water in chemical reactions underscores its importance within the laboratory. It's not just about the fact that water can participate in these reactions, but also how it does so. For example, in a hydrolysis reaction, water can break down a molecule into smaller parts, while in a hydration reaction, it can add to a molecule to change its structure. These reactions are fundamental to many processes in the lab and is key to the synthesis of new compounds to the breakdown of existing ones. Water's role in the lab is not just limited to chemical reactions and solution preparation. It also plays a crucial role in temperature regulation. Thanks to its high specific heat capacity, water can retain and absorb a significant amount of heat, helping to maintain consistent lab temperatures. This property is particularly useful in experiments that require careful heat management. Water is also integral to cooling systems in the laboratory environment, where it helps dissipate heat and prevent overheating, ensuring the smooth operation of these devices. This dual role of water in temperature regulation and equipment cooling highlights its versatility and indispensability in the laboratory. It's not just about the fact that water can absorb and retain heat, but also how it goes about doing that particular practice. The high specific heat capacity of water, which arises from the strong hydrogen bonds between its molecules, allows it to absorb a large amount of heat without a significant increase in temperature.
This is exhausting.
This property is critical to many processes in the lab.
It's a live file.
Somebody want to
making
take a
sure
check
that
on their
optimal
mute?
Conditions for experiments to ensuring the longevity of lab equipment. In the laboratory, not all water is created equal. Depending on the task at hand, different types of water may be used. Tap water, which comes directly from the supply, is used for basic tasks such as washing and rinsing. Distilled water, which is purified through distillation, is used for preparing solutions and cleaning lab equipment. Deionized water, which has undergone ion exchange to remove salts, is used for biological and chemical assays that require a higher level of purity. Lastly, ultra-pure water, which is further treated, distilled, or deionized water, is used for critical applications that demand the highest level of purity. Understanding these different types of water and their uses is crucial for effective lab work. It's not just about the different types of water that exist, but also their applications within the laboratory. The different types of water reflect the different types of needs, from the basic need for cleanliness to the more complex need for purity in sensitive experiments. It is crucial to understand these different types of water and how they're fundamental to effective lab work as well. Tap water is the most basic type of water used in the lab. It comes directly from the municipal supply and is used for simple tasks such as washing and rinsing. However, it is not suitable for sensitive experiments due to the presence of various impurities, which can interfere with results. These impurities can include minerals, salts, and even microorganisms, which can have significant effects on certain experiments. Therefore, while tap water is readily available, it is not necessarily always the best choice to use. Next in line is distilled water, which is a step up in terms of purity. Distilled water is created by boiling tap water and collecting the resulting steam in a clean container. This process, known as distillation, leaves many impurities behind, making distilled water a pure option. It's like taking raw water and refining it through a purification process, much like refining ore to obtain pure metal. While distilled water is far from being the purest form, it's sufficiently pure for many lab tests that need a relatively low level of impurity. These include general washing and rinsing, making certain types of solutions, and even for some less sensitive assays and experiments. Taking the purification process a step further, we have deionized water. Deionization is the process that removes ions from water. Any water, including tap and distilled water, contains dissolved salts, which dissociate into cations and anions. Deionization effectively removes these ions, leaving the water with a markedly lower salt content. In terms of purity, deionized water outperforms distilled water, making it suitable for more sensitive applications, including some types of analytical chemistry. However, while deionization removes salts, it doesn't effectively remove non-ionic organic compounds or microorganisms. Therefore, deionized water still has a limit to its applications. At the pinnacle of water purity, we have ultra-pure water. As its name suggests, ultra-pure water is water that has been extensively purified to remove nearly all of its impurities. This is usually achieved by employing multiple purification steps, such as distillation, deionization, and reverse osmosis, along with other techniques like ultraviolet oxidation or filtration. The aim is to remove not just salts, but also organic compounds, microorganisms, and even dissolved gases to achieve a level of purity that's as close to possible 100%. Ultra-pure water is reserved for high sensitive applications that require the highest purity levels. These include certain biotechnical procedures, high performance liquid chromatography, and other techniques where even the slightest impurity can significantly affect the results. Just as an astronomer needs a high quality telescope to observe distant galaxies, researchers rely on ultra-pure water when they need the utmost precision and accuracy. Water has a wide range of applications within a laboratory. It is used as a solvent for preparing solutions, providing a medium in which various substances can interact. It is essential for cleaning laboratory equipment, helping to remove residuals and prevent contamination. It acts as a medium for biological cultures, providing an environment in which cells can grow. It is also involved in various analytical methods where it facilitates the interaction of different substances and enables the detection and measurement of these substances. Therefore, water is not just a resource, but a tool that enables us to perform a wide range of tasks within the laboratory. It's not just about the fact that water has many uses, but also why it does, the unique properties of water, and also its ability to dissolve various substances to its role in temperature regulation, make it indispensable within the lab. The purity and quality of water of utmost importance in the lab. Different experiments and procedures require different levels of purity. And the presence of impurities can significantly affect the results. Impurities can have detrimental effects on lab equipment, leading to damage and reduced lifespan. Therefore, quality control is vital when it comes to lab water. Regular testing and monitoring are necessary to ensure that the water used in a lab meets the required standards of purity. Therefore, water quality is not just a requirement, but a responsibility that we must all take seriously. It's not just about the fact that water needs to be pure, but also there needs to be an absence of these impurities in water because they can interfere with the results of experiments and ultimately lead to damaging lab equipment or to inaccurate results and increased costs. Achieving the required purity levels for lab water involves the use of different purification systems. As you can see in the chart and the pyramid chart here, these systems can include distillation, deionization, and other treatment methods, each of which removes different types of impurities. Regular testing is crucial to ensure that these systems are working effectively and that the water they produce meets the required standards. Understanding implications of different purity levels for different lab tasks is also important, as it helps to ensure that the right type of water is used for each task. Therefore, water is not just a purification process, but it's also crucial for all the applications that we're going to be using it for. The different purification systems, from distillation units to ionized systems, use different methods to remove different types of impurities. Impurities in water can have significant effects on experimental results and lab equipment. They can influence the data and conclusions of experiments, potentially leading to inaccurate or misleading results. They can also cause damage to laboratory hardware, leading to reduced performance and lifespan. Different types of impurities can be present in water, including organic, inorganic, and bacterial impurities. It is crucial to take the steps to prevent contamination and ensure the purity of lab water. Therefore, dealing with impurities is not just a challenge, but a critical aspect of lab work. The different types of impurities, from organic compounds to inorganic salts to microorganisms, can have different effects on experiments, and is the role of the personnel to make sure that these are not present. There are inherent risks associated with water quality in all of our labs. Poor water quality can compromise the results of experiments and impact the longevity of laboratory tools. It is a shared obligation of all lab personnel to uphold water quality, as it affects everyone in the lab. Everyone has a role in ensuring the purity of lab water, from those who use it in their experiments, those who maintain the purification systems. Poor water quality can lead to inaccurate results and damaged equipment, affecting everyone in the laboratory. Impurities in water can react with substances used in experiments, potentially leading to unexpected results. Waterborne organisms can impact biological samples, potentially leading to contamination and inaccurate results. Impure water can also have corrosive effects on laboratory equipment, leading to damage and reduced longevity and lifespan of the equipment. Furthermore, the additional costs associated with poor water quality, such as the need for equipment repairs or replacement and the potential need to repeat experiments, can be significant. Therefore, dealing with the risks associated with water quality is not just a challenge, but a critical aspect of lab management. The different types of impurities, from organic compounds to inorganic salts or microorganisms, can have different effects on the experiments and lab equipment, and it is part of the lab personnel to ensure that they are taking the precautionary needs to, prevent these implications. Ensuring water purity involves continual learning about water quality and its impacts on lab work for staff. It involves proper handling and storage education to prevent contamination. It involves choosing the right water purification system to achieve the required purity levels. It involves regular testing and quality checks of purification systems to ensure their effectiveness. It involves strictly following lab guidelines for water use to prevent contamination and ensure the integrity of experiments. Therefore, ensuring water purity is not just a task, but a commitment to quality and accuracy. From choosing the right purification system to following proper handling storage procedures, there are many steps involved in ensuring water purity. Understanding these steps and how to implement them is fundamental to effective lab work. In conclusion, water is the backbone of every lab and empowers science. Clear results need clear water, so quality can't be compromised. Regular quality checks are your best insurance for accuracy. Better water leads to better results. Always link water quality to trustworthy outcomes. Therefore, water is not just a resource, but the lifeblood of the lab, enabling us to perform our work and achieve our goals. The unique properties of water, from its ability to dissolve various substances to the role in temperature regulation, make it indispensable in the laboratory, and these are worth repeating. Understanding these properties and how they contribute to the success of our work is fundamental to lab work and to the progress in the industry. I would like to introduce one of our products here that's under our TC brand. It's called ChemForce HPLC
I'm on a call
water.
right now on the other ear.
Oh, sorry. It is a type 1 water suitable for critical cell and tissue culture, DNA sequencing, immunology, pharmacology, trace analysis, and chromatography, molecular biology, and electrochemistry. This product represents our commitment to quality and our understanding of the critical role of water in the lab. It is designed to meet the highest standards of purity, ensuring that your experiments and procedures are not compromised by the previous topics we discussed. We understand the crucial role of water in the lab and the need for high quality, pure water in many applications. This understanding is reflected in our product, which is designed to meet the highest standards of purity and performance. Just like to thank everybody today for my presentation. I will open it up to some questions if anybody has any questions, and I will try my best to answer those. So, or if anybody has any other tips or things that they use in a lab to prevent any type of contamination, ensuring water quality, just how they use it on a daily basis, please feel free to share those opinions, ideas.
Sure, Mike, Frank Vertus. And by the way, nice job on the presentation. I had a couple of questions for you. One was relatively simple, and the other one was just, it sparked my curiosity from a commercial side of things. When you select DI water, what's the most common type used in the lab? I know it depends on testing, but is there a most common type?
The most common type is probably type 2 deionized water. Type 1 and type 2 are similar, but type 2 is definitely by far the most used. They use it a lot in manufacturing processes. We use it in all of our chemical solutions for the most part, and otherwise noted. Sometimes we will use type 1 deionized water or sterile water, or certain types of other purities of water. But, just from my experience, and probably over 90% of our chemical solutions are made from type 2. And, we have the equipment in-house that is serviced by a third party. And we very rarely have any complaints on any of our chemical solutions that are made from this water. So, it is one that is, quite reliable and is quite used, at least in our manufacturing processes.
Thank you. And if I can ask one more, is that
Yeah, sure.
kind of came from the presentation, something I learned today. You mentioned that in the lab, a lot of times people are testing the water versus their current water system. Any idea how long or how often that water system needs to be tested?
So and a lot of it, it's becoming a lot more advanced. So like on our ion exchange units, we actually have, computer systems on each device. We have 4 of them. And each of them, this will record certain parameters without getting too much into details. It'll record certain parameters, and they'll have, in a basic sense, they have 2 lights on them. So we know when something, if you get a double red light, it sends, if you get 1 red light, it'll send a signal to, our vendor supplier, and they'll need to come out and service it. But we also do, morning water checks every morning and throughout the day, ensuring that, the parameters are meeting or exceeding expectations. And when they drop below a certain, parameter specification, therefore that system has to be turned off until it is serviced.
Awesome. Thank you. Appreciate it.
Not a problem. Does anybody else have any questions?
Would you mind explaining to the crowd the difference between HPLC grade water and ACS grade water, just for the difference? I know it's a 2-micron filter, but if you could explain to folks.
Yeah, so a lot of times like ACS reagent grade water, you're going to meet the specifications of ACS. It's going to be for most applications, general applications, like not highly sensitive. You can utilize, ACS, and it's usually going to be, deionized water. And HPLC grade water obviously is going to be used for more highly sensitive experiments. If you're going to be doing a lot of analytical chemistry, much more involved analysis, where you do not want any type of impurities in that particular analysis. You're talking about parts per billion analysis or parts per million, anything. If you have any types of salts, ions, anything within the water, it can, dramatically affect, those outcomes and results. Obviously, both of them go through different types of, purification steps and reverse osmosis, and HPLC goes on to a further step, and there's also, difference of sterile water too, as well, to, for endotoxins, to remove those.
But HPLC grade has to be run through a 2-micron filter to
Correct,
be considered
yes.
HPLC grade. So ACS grade is basically is HPLC grade water after it's run through the 2-micron filter for particulates.
Correct. Yes. So you could technically use that. Now it's just, a lot of waters, even type, different types of water like type 2 and type 1, it's just, there's certain other testing parameters that must be met in order to, to brand it as that. So, like when you're going through reverse osmosis on exchange systems, a lot of times that does remove quite a bit of impurities. It just, what really comes down to is you start talking about the endotoxins that could be in some of these other water types.
And the distillation process, I guess, how do you distill your water? I mean, is it a giant glass distillation system? Is it
For us, we do not. So for us, we do not. We just have deionized water in our manufacturing facilities. So if we're going to be getting distilled water, it would either be made on demand, or we would buy it, make sure that is fresh for an application. But all of our applications are generally deionized water, or we will use HPLC grade water at times. And we do also use sterile water for certain applications. But we, our particular facility, LabChem, is not CGMP. Some of our other facilities under the TCPA brand are. So, most of my experience, although we do use distilled water, is mostly deionized water is that we use for our applications.
what sizes do you mostly sell in the ultra pure water through the up through the grades, I would imagine that people would want to use a smaller size bottle to keep contaminants getting into them in the smaller bottles with the ultra pure stuff. Because the second you open it, you know,
Right. Yeah, I would
Correct,
say,
yes,
Patrick, our most common
exactly.
size is a 4-liter bottle.
I'll let
Even a
Frank
4-liter bottle.
speak on that one, so.
Sorry, Mike, I didn't mean to just jump in.
No,
Patrick,
go
nice to
ahead.
see you, by the way. Yeah, our most common size is 500 mil up to 20 liter, but most common is 1 liter to 4-liter bottle.
for the ultra pure.
Yeah.
Okay, I would think that. Yeah.
Yeah, on the contrary, for our deionized water types, we have sold tote quantities, you know what I mean? But generally we sell a lot of, drum quantities, 200 liter drums, a lot of cubetainers, both 10 liter and 20 liter cubetainer sizes. And we sell 4 liters as well, not a ton of 1 liters when you start getting down to, just the deionized water. So. Does anybody else have any questions?
So while anyone is going ahead and thinking about some more questions or typing out questions, I do want to go ahead and just steal the screen for just a moment.
Yeah, sure, not a problem. I can actually probably stop sharing my screen for now. So.
Where does this normally ship from, by the way? If one last question, please.
Yeah, I can answer that, Patrick. The majority of the water comes from 2 of our locations, one being in Charlotte, and where Mike's housed at Lab Chem today is out of Pittsburgh.
Does it have expiration dates on it?
I believe it's 2 years, right, Mike?
So for our type 2 deionized water, it is 5 years. For type 1, it is 18 months. And I believe for the ultra pure, I believe it's either 18 months or it might be 24. I'm not exactly sure on that one. That is a new product that we just introduced, and it's going to be down at our Charlotte facility because they have some dedicated equipment and able to produce that and also to analyze those.
I can get that for you, Patrick.
Oh, thank you.
You bet.
All right, I'm sorry. I'll stop talking now.
No, it's fine.
Very helpful.
By the way, I'm looking forward to meeting y'all. I'm the new category manager for chemicals and chromatography, so I'm looking forward to meeting y'all at the show if you're coming.
Likewise.
All right, so I do want to take a chance to show you all that TCP is running a promotion. My computer is running just a tad bit slow, but it is in there. There's also a survey in here, as well as literature, web links, and videos. In here as well, up at the top, you will also see on-demand talks. This talk will be on demand by tomorrow, so be sure to bring your customers in and coworkers who you think would benefit from these talks, and it'll be right up here. And you can also take some time to explore the Thomas Center, just hanging out over here. And I'll go ahead and hand it back to see if any questions came up in the chat. Looks like there is one.
I don't know if I can see that. Are you able to read it for me, Heather?
Absolutely. It says, how can you determine which type of water is best used within a certain lab setting?
So when it comes to using different types of grades of water, really, there are established methods, both, referencing wastewater, methods, EPA, USP, ACS, APHA. So you can reference a lot of different, types of resources and to see what kind of, like processes that you're doing, whether it's analysis, whether it's manufacturing. And you also have to look at, who your potential customers are or your clientele, is as well. These are all critical, factors in deciding, what is important for your type of process, because you do not want to get too pure of water, maybe it's, you have to kind of balance it, what is, giving the best, something that's effective, yet something that's cost effective as well, and something, providing the customers, with something that, is a quality product, ensuring that the water quality is good and that it doesn't affect anything else going into that, that solution.
Hey, Mike, what does it mean? What does it mean if it's too pure of water? You had alluded to that, not to put you on the spot, but
It's not so much too pure. You can never use too pure. It's kind of like using like a certain type of chemical. They have different grades of chemicals. They have technical grades of chemicals. They have ACS, meeting ACS specifications. They have, other ones like food grade as well. Then they have like trace metal grades. They have all these. It's not so much being too pure. I think it's, you have to find a balance, because if if you're trying to, if you start getting on the side of profits and other things, because a lot of products are more like when they're, purifying products, not just water, but other products, they'll take it from the same, starting, it could be something as simple as sodium hydroxide. You have the same sodium hydroxide, then you could have technical grade. You're going to run certain tests on that. Then you have ACS, and you're going to run other ones on that as well. And when you get further down in the higher purity levels, they run some other ones. But, sometimes depending on what your customer needs or what you need, and what you're making or manufacturing, you may not necessarily need, something, maybe one of the specifications on a particular, chemical or water is, you're talking parts per billion. You need to be down that low. Can you still produce a quality product? Maybe you want to go in parts per million, and you start looking, because cost starts getting quite expensive the higher pure chemicals or water that you go with. But it's also, crucial to make sure that you have the right grade for those applications.
okay, thank you.
Yep.
Is there
see
another
one more
question on the-
I see that blood bank water.
Okay.
I'm not, I'll be honest with you, I'm not exactly, I'm not familiar with blood bank water. I'm assuming it would have to be something that would probably have to be very purified, and also, suitable for, it would have to probably most likely be sterile water. That would be my guess, if it's going to be used for any type of application, for food, drug, or human use, or any type of, possibly even injection or anything like that.
Yeah, I was just going to comment on that as well. I think I'm off of mute. Yeah, water for injection or blood bank water is something that we don't handle right now.
Yeah.
And anything for human use isn't anything that we would produce at this point.
Yeah, we don't know water for injection. We do not, we do not produce any of that. So.
I think that's all the questions. Anyone else have a last minute question in there?
Also, if people do have any other questions, our location and Pittsburgh, and also our location, most of our locations have dedicated support, technical teams. So you guys, anybody on the call, or if you have friends or anybody in the industry that has a particular question, even, completely unrelated to water, about any of our chemicals, you're more than welcome to call in, and you can talk to, a group of technical staff, which they are normally chemists. So they do have a good technical background and understanding of, the catalog offerings, or any type of, custom quoted things, it's, so we can provide information regarding that, and our capabilities, capacities as well. So.
Well, Heather, thank you for the invite. Mike, congratulations. That was a well done presentation. And,
Oh, well, thank you. I appreciate it.
Thanks for joining today. We're here to help you in any way, shape, or form relative to your chemistries.
Yeah. No, thank you to everybody that joined. Thank you for listening. I appreciate it. I appreciate the questions, and hopefully I gave some suitable answers, and you did learn some things in the presentation. So I thank you, for being here.
Yeah. Awesome. Thank you guys so much for joining us, and have a great rest of your day.
You too.
Thank you.
Heather, did you need me to